Right now, at this very moment, beneath the waves of our blue planet, there exists a world so vast and mysterious that it makes outer space seem familiar by comparison. More than 95% of our ocean remains unexplored, a realm of gentle giants, living lights, and ancient wisdom that has been quietly thriving in darkness for hundreds of millions of years. Everything we think we know about life on Earth barely scratches the surface of what lies beneath. Welcome to Sleep About Science. Tonight we're diving deep into the most peaceful, profound wilderness on our planet, the deep sea. And if you drift off to sleep while listening, that's perfectly wonderful. In fact, there's something rather fitting about falling asleep to stories of the deep ocean, where so much of life moves slowly, deliberately, in a rhythm as ancient as the tides themselves. Before we begin, please make yourself comfortable, pull up your covers, adjust your pillow, let your breathing slow and deepen. And remember, this is educational content, not medical advice. If you haven't subscribed yet, you might want to, so you never miss these gentle journeys into the wonders of our natural world. Now, let's descend together into the blue heart of our planet, where pressure and darkness have created something extraordinary, a world of quiet miracles. The deep sea begins where sunlight ends, roughly 200 meters below the surface, but it's not an empty void waiting down there. It's home. Home to more species than we've yet discovered. Home to ecosystems that have been perfecting the art of survival for longer than land has existed. Home to creatures that seem to have been dreamed into existence by the ocean itself. Picture this: if you can monitor the water around you is perfectly still, dark as velvet, and yet it pulses with life. Bioluminescent creatures drift past like living stars, their bodies generating light through chemical reactions so efficient that scientists are still studying them, trying to understand how these animals create illumination without heat, without waste, without the friction that makes our human-made lights so imperfect. The vampire squid glides through this darkness with the grace of a ballet dancer, its name far more frightening than its nature. When threatened, it doesn't attack me, It turns itself inside out, revealing soft spines that make it look like a spiky ball, a gentle creature's ingenious way of saying, "Please leave me alone." Its eyes are the largest relative to body size of any animal on Earth, evolved to capture every precious photon of light in a world where light is rarer than gold. Down here, at depths where the pressure could crush a human instantly, glass sponges grow in gardens that stretch for miles. These aren't the sponges you might imagine. They're made of silica, the same material as glass, and they filter water so slowly, so patiently, that some of them are thought to be over 10,000 years old. They were already ancient when humans first began to farm, already wise when we built our first cities. They simply sit on the seafloor breathing water, filtering nutrients, being. The giant tube worms cluster around hydrothermal vents like flowers around a warm hearth, their bodies reaching lengths of 8 feet or more. They have no mouth, no stomach, no way to eat in any way we would recognize. Instead, they've formed partnerships with bacteria that live inside them, bacteria that can take the chemicals spewing from the Earth's core and transform them into food. It's a collaboration so intimate, so essential, that neither partner can survive without the other. They've been perfecting this relationship for millions of years, long before we learned to cooperate with each other. In the deepest trenches of our ocean, where the pressure is over 1,000 times greater than at sea level, amphipods no bigger than your thumb go about their daily lives completely unbothered by conditions that would be instantly fatal to almost any other form of life. They've learned to make their cell membranes flexible, their proteins resistant to crushing forces. They're not struggling against the pressure nears, they've adapted to it so completely that they couldn't survive anywhere else. The deep is their home, and they're perfectly peacefully at home there. The deep-sea anglerfish carries her own lantern, a bioluminescent lure that dangles in front of her mouth like a fishing line cast into the darkness. The light comes from bacteria living in her lure, bacteria that she feeds and protects in exchange for their gentle glow. In the deepest places, where finding food requires patience measured in months rather than hours, she can afford to wait. Her metabolism has slowed to match the rhythm of the deep, where time moves differently, where survival is less about speed and more about endurance. Jellyfish in the deep ocean grow to sizes that would astonish you. The lion's mane jellyfish can have tentacles longer than a blue whale, trailing through the water like silk scarves in slow motion. But down here, even the largest predators move with a dreamlike quality, their bells pulsing slowly, hypnotically, as they drift through the dark water. They don't rush. They don't need to. In the deep sea, patience isn't just a virtue, it's the foundation of life itself. The Yeti crab, discovered only in recent years, lives near hydrothermal vents, and grows gardens of bacteria on its arms. It waves these hairy appendages through the water, cultivating its bacterial partners, then scrapes them off to eat when it needs nutrition. It's farming, essentially one of the most sophisticated forms of agriculture on Earth, practiced by a creature no bigger than your hand, in darkness, deeper than we can easily imagine. Barrel-leaf fish swim through the deep with heads so transparent you can see their brains, their tubular eyes pointing upward like periscopes, watching for the silhouettes of prey against the faint light filtering down from far above. Their eyes can rotate within their transparent skulls, allowing them to look forward when they need to feed. They're living submarines, perfectly designed for life in three-dimensional darkness. The giant isopods of the deep sea are related to the pill bugs you might find in your garden, but they've grown to the size of footballs in the high-pressure, low-temperature world of the deep ocean. They move slowly across the seafloor like armored vacuum cleaners, processing the marine snow, the gentle rain of organic matter that drifts down from the surface world. They can survive for years without food, their metabolism so slow that they barely seem alive, yet they are among the most successful scavengers in the deepest places on Earth. Dumbo octopuses flutter through the water using ear-like fins, their movements so graceful they seem to be flying rather than swimming. They live deeper than any other octopus, in a world where the water is just above freezing and darker than the space between stars, yet they move with such gentle elegance that watching them feels like meditation, their 8 arms trailing behind them as they pulse through the water with unhurried purpose. The deep sea is filled with creatures that glow. 90% of animals below 1,000 meters can produce their own light. But this isn't the harsh electric light of our surface world. It's a soft blue-green luminescence, the color that travels farthest in water, the color that speaks most clearly in the language of the deep. Some use it to communicate, flashing messages we don't yet understand. Others use it to confuse predators, ejecting clouds of glowing particles like underwater fireworks. Still others use it simply to see, carrying their own gentle lanterns through the eternal night. In the deepest parts of the ocean, where no light has ever penetrated, communities of bacteria thrive around underwater hot springs, creating the foundation for entire ecosystems. These bacteria don't need sunlight, they feed on chemicals, transforming hydrogen sulfide and methane into the energy of life. They're the primary producers in a world without plants, the basis of food webs that exist completely independently of the sun. They've been doing this for billions of years, long before photosynthesis was invented, quietly proving that life can find a way almost anywhere. The giant spider crabs of the deep have legs that span 12 feet from tip to tip, yet they move across the seafloor with surprising gentleness, their movements deliberate and careful. Despite their intimidating size, they're essentially underwater gardeners, using their precise legs to pick small morsels from the sediment, cleaning the seafloor as they feed. They can live for over a century, growing slowly, patiently, measuring their lives not in years but in decades. Deep-sea fish have learned to be efficient in ways that would make an engineer weep with admiration. Many have scaleless, gelatinous bodies that offer no resistance to the water around them. Others have reduced their skeletons to the bare minimum, their bodies more water than solid matter. They don't fight the pressure, they become the pressure, their internal pressure, matching exactly the crushing force of the water around them. They're liquid living in liquid, perfectly balanced. The marine snow that falls constantly through the water column is like a gentle, eternal blizzard. It's made up of tiny flakes of organic matter, dead plankton, fecal pellets, fragments of larger organisms, all drifting downward in a slow-motion cascade that can take weeks to travel from the surface to the seafloor. This snow feeds entire communities in the deep, providing a steady, reliable source of nutrition that has been falling for millions of years. It's the ocean's way of recycling, ensuring that nothing is ever truly wasted. Hydrothermal vents create oases in the deep-sea desert, spots where the Earth's core heat meets the ocean's cold, creating environments so rich with life that they rival tropical rainforests in their biodiversity. The water around these vents can reach temperatures of over 400 degrees Celsius, hot enough to melt lead, yet just inches away, the water returns to its normal near-freezing temperature. Life thrives in this gradient, finding ways to harness both the heat and the cold. The deep-sea mushroom Dendrogramma was discovered so recently that scientists are still trying to figure out what it actually is. It looks like a mushroom, but it's an animal, one so unusual that it might represent an entirely new phylum of life. It simply sits on the seafloor, quietly filtering water, having survived for millions of years without anyone noticing it was there. It's a reminder that the deep sea still holds secrets we can't even imagine. Siphonophores drift through the deep water like living galaxies, their bodies stretching for lengths that can exceed 150 feet, longer than a blue whale. But they're not single animals. They're colonies, communities of tiny individuals, each specialized for a particular function, some for swimming, some for feeding, some for reproduction, some for defense. They're cities that swim, cooperative societies that have perfected the art of working together. The deep-sea cucumber moves across the seafloor like a living vacuum cleaner, processing sediment and extracting nutrition from what most creatures would consider waste. They're the janitors of the deep sea, cleaning up the seafloor, recycling nutrients, keeping the deep ocean healthy. Some of them can eject their internal organs when threatened, then regrow them later, a defense mechanism so extreme it seems like science fiction, yet it works perfectly in their slow-paced world. In the deepest trenches, where the seafloor drops away into chasms deeper than Mount Everest is tall, specially adapted fish continue to thrive. The deepest fish ever recorded, the Mariana snailfish, lives at depths where the pressure is so intense that protein should denature, where life should be impossible according to our understanding of biology. Yet there it is, swimming peacefully through the crushing darkness, its body perfectly adapted to conditions that would destroy almost any other living thing. The deep sea is quiet in a way that's hard to imagine. Sound travels differently down there, farther, clearer, but muffled by the immense pressure. The songs of whales can travel for thousands of miles through the deep sound channel, a layer of water where sound waves get trapped and can circle the entire globe. It's a natural internet, a communication network that whales have been using for millions of years to stay in touch across the vast distances of the ocean. Deep-sea corals grow without sunlight, building reefs in the darkness that can be thousands of years old. They feed by filtering tiny organisms from the water, growing so slowly that some colonies are older than recorded human history. These coral reefs provide homes for communities of fish and invertebrates that exist nowhere else, creating biodiversity hotspots in the deep ocean that we're only beginning to understand. The vampire squid's scientific name, Vampyroteuthis infernalis, means vampire squid from hell, but nothing could be further from the truth about this gentle creature. When it feeds, it extends filaments covered in tiny hooks, not to hunt living prey, but to collect marine snow, the organic matter that drifts down from above. It's a peaceful filter feeder, content to wait for food to come to it, embodying the patient rhythm of deep-sea life. Bone-eating worms, Ozodiacs, have one of the most remarkable life cycles in the ocean. When a whale dies and sinks to the seafloor, these worms colonize the bones, using acid to dissolve the bone and extract lipids that the whale stored there during its lifetime. A single whale carcass can support a community of these worms for decades, creating an oasis of life around death, transforming the whale's final gift into sustenance for an entire ecosystem. The deep-sea dragonfish has a mouthful of transparent teeth. It is invisible daggers that help it catch prey without being seen. Its body is black as the void around it, and it can produce red bioluminescent light, a color that most deep-sea creatures can't see. It's like having night vision goggles in a world where everyone else is blind to that part of the spectrum. It moves through the water like a shadow with eyes, perfectly camouflaged until the moment it strikes. Deep-sea gigantism is a phenomenon where creatures grow much larger than their shallow water relatives. Giant isopods, giant amphipods, giant sea spiders. The deep ocean seems to encourage bigness, perhaps because food is so scarce that when it's available, there's an advantage to being large enough to process large meals. These gentle giants move slowly through their world, their size a adaptation to the feast or famine lifestyle of the deep. The deep-sea hatchetfish has a body so thin it's almost two-dimensional, covered in light-producing organs called photophores that line its belly. When predators look up at it from below, the hatchetfish can match the faint light filtering down from above, essentially making itself invisible through counter-illumination. It's active camouflage, biological stealth technology perfected over millions of years. Xenophyophores are among the largest single-celled organisms on Earth, some growing to the size of dinner plates. These gentle giants live on the deep seafloor, building themselves houses out of sand grains and marine debris, creating structures that can persist for decades. They're living architecture, single cells that construct their own homes, proving that you don't need to be multicellular to be complex. The deep-sea cucumber fish has reduced its skeleton so much that it's barely there. It's essentially a swimming bag of muscle and organs, perfectly adapted to the high-pressure environment where rigid structures would be a liability. It moves through the water like liquid mercury, its body conforming to the pressure around it, a master of fluid dynamics. In the deep ocean, many creatures practice vertical migration, one of the largest movements of biomass on Earth. Every night, billions of small organisms swim upward from the deep to feed in the productive surface waters, then return to the depths before dawn. This migration transfers nutrients from the surface to the deep, connecting the two worlds in an endless cycle of movement that has been going on for millions of years. The gulper eel can unhinge its massive jaw to swallow prey larger than its own body, its stomach stretching to accommodate meals that might have to last for months. In a world where food is scarce, the ability to eat whatever you encounter, regardless of size, is a profound advantage. It's a living lesson in making the most of opportunities, no matter how rare they might be. Deep-sea fish often have huge eyes relative to their body size, evolved to capture every available photon in their dark world. But some fish have gone the opposite direction, losing their eyes entirely and relying on other senses. The deep-sea cusk eel navigates by feeling, tasting, and sensing electrical fields, moving through its world with senses we can barely imagine. The deep ocean contains the largest living spaces on Earth. The abyssal plains stretch for thousands of miles, flat expanses of sediment that are larger than continents, yet teeming with microscopic life. These plains are like underwater prairies, supporting communities of bacteria, foraminifera, and small invertebrates that form the foundation of deep-sea food webs. Deep-sea creatures often have gelatinous bodies that are mostly water, making them neutrally buoyant so they don't have to waste energy swimming just to stay in place. They drift through the water column like living clouds, their bodies so transparent that they're nearly invisible even when you're looking directly at them. They've achieved something close to weightlessness, floating through their three-dimensional world with minimal effort. The deep-sea anglerfish male is tiny compared to the female, and when he finds a mate, he bites onto her and eventually fuses with her body, becoming essentially a sperm-producing appendage. It sounds extreme, but in a world where finding a mate in the vast darkness is almost impossible, this strategy ensures that reproduction can happen when the opportunity arises. It's evolution's solution to the problem of finding love in the dark. Hydrothermal vent communities are among the most productive ecosystems on Earth, rivaling tropical rainforests in their density of life. But unlike rainforests, which depend on sunlight, these communities are powered entirely by chemosynthesis, the process of making food from chemicals rather than light. They're proof that life doesn't need the sun. That energy can be found in the most unlikely places. The deep-sea snailfish holds the record for the deepest living fish, found at depths of over 26,000 feet in the Mariana Trench. At those depths, the pressure is over 1,000 times greater than at sea level, yet these fish swim normally, their bodies perfectly adapted to conditions that would crush surface-dwelling creatures instantly. They're living proof that life can adapt to almost any environment, no matter how extreme. Deep-sea mushrooms, animals that look like fungi, menace filter water through their bodies so slowly that they barely seem to be alive. They can remain motionless for hours or even days, patiently waiting for food particles to drift within reach. They embody the deep-sea philosophy of conservation, doing only what's necessary, wasting no energy on unnecessary movement. The giant red mysid shrimp grows to lengths of over a foot, enormous for a creature that's typically thumbnail-sized in shallow waters. It swims through the deep ocean with grace, using its feathery appendages to propel itself through the water in slow motion. Its red color, which appears black in the blue-filtered light of the deep sea, makes it nearly invisible to both predators and prey. Deep-sea mining is a growing concern among scientists, not just because of the potential environmental damage, but because we're still discovering new species faster than we can study them. Every deep-sea expedition reveals creatures never seen before, ecosystems we didn't know existed, relationships between species that challenge our understanding of life itself. We're potentially destroying things before we even know they exist. The deep-sea glass sponge reefs of the Pacific Northwest are among the oldest living things on Earth, some specimens estimated to be over 9,000 years old. They grow incredibly slowly, adding just millimeters to their height each year, but they've created underwater mountains, three-dimensional structures that provide homes for countless other species. They're living cathedrals, built grain by grain over millennia. The deep ocean acts as a massive carbon sink, absorbing carbon dioxide from the atmosphere and storing it in the deep water for hundreds or thousands of years. The deep-sea organisms play a crucial role in this process, their bodies incorporating carbon that eventually sinks to the seafloor when they die. They're climate regulators, helping to moderate the Earth's temperature through their simple existence. Bioluminescence in the deep sea serves many purposes minus communication, camouflage, hunting, defense, but it also creates one of the most beautiful light shows on Earth. The deep ocean twinkles and glows like a living galaxy, creatures flashing messages in languages we don't yet understand, creating patterns of light that would take your breath away if you could see them. The deep-sea sea pig, a type of sea cucumber, travels across the seafloor in herds, like underwater cattle grazing on the organic matter in the sediment. They move together in groups that can number in the thousands, following chemical trails and staying in touch through methods scientists are still trying to understand. They're social creatures in a world where sociability might seem impossible. Deep-sea creatures often have slow metabolisms, allowing them to survive on very little food for long periods. Some deep-sea fish can go months without eating, their bodies operating on minimal energy, their movements slow and deliberate. They've mastered the art of conservation, doing more with less, surviving in a world where waste means death. The deep-sea chimera, also known as the ghost shark, is more closely related to sharks and rays than to bony fish, but it looks like something from another planet. It glides through the deep water with wing-like fins, its whip-like tail trailing behind it, its large eyes adapted for life in perpetual darkness. It's a living fossil, largely unchanged for millions of years. Many deep-sea creatures practice sit-and-wait predation, remaining motionless for long periods until prey comes within range. This strategy conserves energy in an environment where energy is precious, but it requires incredible patience. These predators have learned to think in geological time, measuring their hunts not in minutes but in hours or days. The deep-sea bamboo shark is one of the few sharks that can survive in the deep ocean's low-oxygen environment. It has adapted to extract every possible bit of oxygen from the water, its gills working with incredible efficiency. It moves slowly through its world, conserving energy, proving that even apex predators must bow to the constraints of the deep. Deep-sea creatures often have transparent blood, lacking the red hemoglobin that carries oxygen in surface-dwelling animals. Instead, they've evolved different ways to transport oxygen through their bodies, some using the ocean water itself as their circulatory fluid. They've reinvented one of the basic functions of life, finding new solutions to ancient problems. The deep-sea fangtooth fish has the largest teeth relative to body size of any fish in the ocean, yet it's only about 6 inches long. Its teeth are so large that it has special sockets in its skull to accommodate them when it closes its mouth. Despite its fearsome appearance, it's actually quite small and fragile, proof that in the deep sea, looking dangerous might be more important than being dangerous. Deep-sea trenches are the deepest places on Earth, some plunging to depths of over 36,000 feet. These trenches are formed where tectonic plates collide, creating some of the most geologically active areas on the planet. Yet even in these extreme environments, life persists, adapted to pressures and conditions that would destroy most life forms. The deep-sea coffinfish gets its name from its box-like shape, but it's actually a master of camouflage. When threatened, it can inflate its body and spread its fins to look like a piece of debris or a rock on the seafloor. It embodies the deep-sea strategy of hiding in plain sight, using deception rather than speed to avoid predators. Many deep-sea creatures have bioluminescent lures, using light to attract prey in the darkness. But these lures aren't just simple lights. They're sophisticated organs that can produce different colors, flash in complex patterns, and even mimic the movements of small prey animals. They're living neon signs, advertising in the language of light. The deep-sea sea angel is a type of swimming sea slug that moves through the water with wings like an underwater butterfly. Its movements are hypnotically graceful, its transparent body barely visible in the dark water. It feeds on sea butterflies, another type of swimming mollusk, in a predator-prey relationship that plays out in slow motion in the deep ocean's eternal night. Deep-sea woodfalls are oases in the deep ocean desert. When trees are swept out to sea and sink to the deep-sea floor, they create temporary ecosystems that can last for decades. Specialized bacteria decompose the wood, creating an environment rich in nutrients that attracts a succession of different species over time. These woodfalls are like time capsules, preserving pieces of the terrestrial world in the deep sea. The deep-sea spoonworm can extend its feeding proboscis to lengths many times its own body size, sweeping across the seafloor like a living vacuum cleaner. It processes enormous amounts of sediment, extracting nutrition from what appears to be lifeless mud. It's a master recycler, finding sustenance in the waste products of the upper ocean. Deep-sea creatures often have reduced or absent swim bladders, the gas-filled organs that help fish control their buoyancy. In the high-pressure environment of the deep sea, gas-filled organs would be compressed to uselessness or would require enormous amounts of energy to maintain. Instead, Deep-sea fish rely on oils and other density-reducing adaptations to achieve neutral buoyancy. The deep-sea dumbbell jellyfish has a unique body plan, with two bell-shaped ends connected by a narrow neck. This design allows it to swim in two directions simultaneously, a useful adaptation in a three-dimensional environment where food and threats can come from any direction. It's evolution's solution to the problem of living in infinite space. Many deep-sea fish have expandable stomachs that can accommodate prey much larger than the fish themselves. In an environment where meals are few and far between, the ability to eat whenever the opportunity arises, regardless of the size of the prey, is a crucial survival skill. They're living storage units, carrying their next several meals inside them. The deep-sea telescope fish has tubular eyes that can be pointed in different directions, allowing it to watch for prey above while simultaneously watching for predators below. This dual-direction vision is common in the deep sea, where threats and opportunities can come from any angle in the three-dimensional darkness. Deep-sea hydrothermal vents create their own weather systems, with hot water rising and cool water sinking, creating currents and flow patterns that distribute nutrients and heat throughout the vent community. These underwater weather systems are predictable enough that vent organisms have adapted their life cycles to take advantage of them. The deep-sea giant amphipod grows to sizes that would be impossible in shallow water, some reaching lengths of over a foot. These creatures are essentially underwater insects, related to the small beach hoppers you might find in seaweed, but grown to monster size in the food-rich environment around whale falls and other deep-sea bonanzas. Deep-sea fish often have antifreeze proteins in their blood and tissues, allowing them to survive in water that's just above the freezing point. These proteins work by binding to ice crystals and preventing them from growing, essentially giving the fish natural antifreeze that's more efficient than anything humans have developed. The deep-sea bigfin squid has arms and tentacles that can extend to lengths of over 20 feet, trailing behind it like underwater streamers as it moves through the water. It holds its arms in a distinctive position, spread wide like the spokes of an umbrella, using them to sense vibrations and chemical cues in the water around it. Deep-sea methane seeps create communities based on chemosynthesis, similar to hydrothermal vents but powered by methane instead of hydrogen sulfide. These seeps can persist for thousands of years, creating stable ecosystems that support tube worms, clams, and bacterial mats. They're proof that life can find energy sources we never imagined. The deep-sea rattail fish, despite its name, is actually quite graceful, with a long tapering tail that it uses for propulsion and a sensitive snout that it uses to probe the seafloor for food. It's one of the most common fish in the deep ocean, a generalist that has found ways to survive in almost every deep-sea environment. Many deep-sea creatures are hermaphroditic, possessing both male and female reproductive organs. In an environment where finding a mate is extremely difficult, the ability to reproduce with any other member of your species, or even by yourself, is a tremendous advantage. It's evolution's solution to the loneliness of the deep. The deep-sea vampire squid can turn itself inside out when threatened, revealing a spiky, intimidating exterior that's actually quite harmless. This inside-out configuration exposes photophores that create a spectacular light show designed to confuse and deter predators. It's biological special effects, using light and transformation to survive. Deep-sea sediments accumulate incredibly slowly, sometimes just millimeters per 1,000 years. This means that the seafloor preserves an incredibly detailed record of Earth's history, with layers that record climate changes, volcanic eruptions, and mass extinctions going back millions of years. The deep seafloor is Earth's memory, storing information about our planet's past. The deep-sea snipe eel has jaws that can unhinge and extend far beyond its head, allowing it to catch prey that would otherwise be too large or too far away. Its body is incredibly elongated, like a living ribbon that undulates through the water with serpentine grace. It's perfectly adapted for life in the open water column, where prey is sparse but space is infinite. Deep-sea creatures often have reduced skeletons and soft, gelatinous bodies that offer no resistance to the crushing pressure around them. They don't fight the pressure, they become one with it, their bodies essentially liquid living in liquid. It's a profound adaptation, giving up rigidity for fluidity, structure for flexibility. The deep-sea gulper shark can extend its pharynx like a vacuum cleaner, sucking up prey from the seafloor or from crevices in the rock. Despite being a shark, it's quite small and moves slowly through its environment, conserving energy and relying on suction feeding rather than active pursuit to catch its prey. Many deep-sea jellyfish never touch the seafloor or the surface, spending their entire lives drifting in the open water column. They're permanent residents of inner space, three-dimensional nomads that follow currents and food sources through the vast middle waters of the ocean. They embody the freedom of living in infinite space. The deep-sea cookie-cutter shark takes perfectly round plugs of flesh from much larger animals, whales, dolphins, large fish, using its specialized teeth and suction-cup mouth. It's like a living hole punch, taking just what it needs and then disappearing back into the darkness. Its bite marks are found on animals throughout the world's oceans, proof of its global presence. Deep-sea whale falls go through predictable stages of decomposition, each attracting different communities of organisms. First come the scavengers, then the bacteria that break down the soft tissues, then the bone-eating worms that can persist for decades, slowly consuming the whale's skeleton. It's a succession of life arising from death, a multi-decade feast in the desert of the deep. The deep-sea chimera has been called a living fossil, largely unchanged for hundreds of millions of years. It glides through the deep water with wing-like pectoral fins, its whip-like tail trailing behind it, looking more like an underwater bird than a fish. It's a reminder that some body plans are so perfect, they never need to change. Deep-sea bacteria form the foundation of most deep-sea food webs, converting chemicals into energy through processes we're still learning to understand. They're the plants of the deep sea, the primary producers that make life possible in a world without sunlight. They prove that photosynthesis isn't the only way to power an ecosystem. The deep-sea basket star spreads its branching arms like an underwater tree, filtering plankton and organic particles from the water. Its arms can branch and rebranch dozens of times, creating a complex network that looks more like a plant than an animal. It's a living net, patiently waiting for food to drift within reach of its thousands of tiny arm tips. Many deep-sea fish have huge mouths relative to their body size, an adaptation to the feast-or-famine lifestyle of the deep ocean. When food is available, they need to be able to eat as much as possible, regardless of what size it might be. Their expandable jaws and stomachs allow them to take advantage of any feeding opportunity. The deep-sea single-celled xenophyophores build intricate tests, external skeletons, out of sand grains, sponge spicules, and other marine debris. These structures can be incredibly complex, with chambers and tunnels that seem to serve no obvious purpose. They're art created by single cells, beauty arising from the simplest forms of life. Deep-sea trenches act as traps for organic matter, concentrating food resources that would otherwise be spread across vast areas of seafloor. This concentration of food supports some of the highest biomass densities in the deep ocean, creating ecosystems that are rich and diverse despite the extreme conditions. The deep-sea lizardfish lies in wait on the seafloor, perfectly camouflaged until prey comes within striking distance. Its attack is lightning fast, a sudden explosion of movement in a world where most things happen slowly. It embodies the deep-sea strategy of patience punctuated by brief moments of intense activity. Deep-sea coral gardens grow on seamounts and ridges, creating underwater forests in the darkness. These corals don't need sunlight. They feed by filtering small organisms from the water, growing incredibly slowly but persisting for centuries. They create three-dimensional habitat in a mostly two-dimensional world, providing homes for countless other species. The deep-sea lanternfish performs one of the most remarkable migrations on Earth, swimming from depths of several thousand feet to near the surface every night to feed, then returning to the deep before dawn. Billions of these fish participate in this migration, creating one of the largest movements of biomass on the planet. Deep-sea creatures often have reduced pigmentation, appearing colorless or transparent in a world where color serves no purpose. But many retain patches of red pigment, which appears black in the deep ocean's blue filtered light, providing perfect camouflage. They're masters of invisibility, using the physics of light and water to disappear. The deep-sea stoplight loosejaw has red bioluminescent organs that it can use like a flashlight, illuminating prey that can't see red light. It's like having night vision goggles in a world where everyone else is blind to that color. This private wavelength of light gives it a tremendous advantage in the competition for food. Many deep-sea fish have photophores light-producing organs, arranged in species-specific patterns along their bodies. These patterns serve as identification signals, allowing members of the same species to recognize each other in the darkness. They're living barcodes, using light to communicate identity in a world where visual cues are rare. The deep-sea football fish gets its name from its round, inflated appearance, but it's actually a highly specialized predator. Its huge mouth can unhinge to swallow prey nearly as large as itself, and its bioluminescent lure can be extended far in front of its mouth to attract prey from a distance. Deep-sea communities around cold seeps can persist for thousands of years, creating some of the most stable ecosystems on Earth. Unlike the boom-bust cycles common in surface ecosystems, these deep-sea communities maintain steady populations over geological timescales, proving that stability is possible in the natural world. The deep-sea gulper eel's massive mouth is lined with tiny teeth that point inward, ensuring that anything that enters can't escape. Its jaw is so large that it makes up about a quarter of its total body length. It's a living trap, perfectly designed to capture whatever prey might be available in the food-poor environment of the deep ocean. The deep-sea sea butterfly swims through the water with wing-like appendages, its shell spiraling in perfect mathematical proportions that would make an architect weep with admiration. These tiny mollusks create shells of such delicate beauty that they seem too fragile for the harsh deep-sea environment, yet they've been thriving in these conditions for millions of years, proving that sometimes delicacy is its own form of strength. In the deepest parts of the ocean, pressure becomes almost a living thing itself, not just a physical force, but an environmental sculptor that has shaped life in ways we're only beginning to understand. The deepest living fish have proteins that are folded in completely different ways than surface proteins, molecular origami that can function under pressures that would destroy normal biological molecules. The deep-sea sea pen looks exactly like an old-fashioned quill pen, standing upright on the seafloor and swaying gently in the current. But it's not a single animal both, it's a colony, hundreds of tiny polyps working together to filter food from the water. Each polyp has a specialized function, some for feeding, some for reproduction, some for defense. They've created a living writing instrument that authors its own story on the seafloor. Deep-sea brine pools are underwater lakes, areas where extremely salty water is so dense that it sits on the seafloor like a separate body of water. Fish can swim over these pools as if flying over a lake, and specialized bacteria thrive at the interface between the brine and the regular seawater. These underwater lakes have their own shorelines, their own ecosystems, their own unique chemistry. The deep-sea crossotter jellyfish moves with such ethereal grace that it seems to dance rather than swim, its bell pulsing in slow, hypnotic rhythms that match the deep ocean's patient heartbeat. It can remain motionless for hours, drifting with the current, then suddenly spring into action when prey approaches. It embodies the deep-sea principle of conserving energy until the moment when energy is most needed. Deep-sea seamounts rise from the abyssal plains like underwater mountains, creating islands of biodiversity in the deep ocean desert. These underwater peaks support their own unique ecosystems, with species that exist nowhere else on Earth. Many seamounts have never been explored, never been seen by human eyes, harboring communities of life that have been evolving in isolation for millions of years. The deep-sea frilled shark is often called a living fossil, virtually unchanged for 80 million years. It moves through the water like a prehistoric serpent, its primitive gill slits flaring as it breathes, its needle-sharp teeth designed for grasping squid and other soft-bodied prey. It's a window into the ancient ocean, a survivor from the time when dinosaurs walked the earth above. Deep-sea fish often have blood that contains antifreeze glycoproteins, natural antifreezes that prevent ice crystals from forming in their bodies. These proteins are so efficient that they can prevent freezing at temperatures well below the normal freezing point of bodily fluids. They're nature's solution to life in the near-freezing waters of the deep ocean. The deep-sea dumpling squid gets its name from its round, plump appearance. But don't let its cute looks fool you. It's a sophisticated predator with highly developed eyes and lightning-fast tentacles. It hovers in the water column like a living balloon, using its fins to maintain perfect position while it waits for prey to drift within reach of its lightning-quick strike. Deep-sea hydrothermal vent fields can extend for miles, creating underwater cities of life powered by the Earth's internal heat. These vent fields have their own neighborhoods, biomes, areas dominated by different species, territories marked by chemical gradients rather than physical boundaries. The chemistry of the water changes from block to block, creating microhabitats as distinct as city neighborhoods. The deep-sea phantom anglerfish is so transparent that you can see its internal organs, its bones, even its brain through its clear skin. This transparency makes it nearly invisible in the water column, a ghost fish that appears and disappears like a mirage. Its bioluminescent lure glows like a will-o'-the-wisp in the darkness, attracting prey to a predator they can barely see. Many deep-sea creatures practice kleptoplasty meti. They steal chloroplasts from algae and incorporate them into their own cells, essentially becoming part plant. These borrowed solar panels allow them to supplement their diet with photosynthesis, creating their own food from light when they venture into the upper layers of the ocean. It's biological piracy turned into a survival strategy. The deep-sea ping-pong tree sponge gets its name from its ball and cup structure, but it's actually one of the most efficient filter feeders in the ocean. Water flows through its body in carefully designed patterns that maximize nutrient extraction while minimizing energy expenditure. It's a living lesson in fluid dynamics, evolution's solution to the problem of feeding in nutrient-poor water. Deep-sea fish larvae often look nothing like their parents, living completely different lifestyles in the upper ocean, before transforming into deep-sea forms. Some undergo metamorphoses so dramatic that scientists initially thought the larvae and adults were different species. It's as if each fish lives two completely different lives, one in the light and one in the darkness. The deep-sea slickhead fish has such smooth, scaleless skin that it offers almost no resistance to water flow. Its body is so streamlined that it can glide through the water with minimal energy expenditure, like a living torpedo designed by millions of years of evolution. Its large eyes are perfectly adapted for spotting the silhouettes of prey against the faint light filtering down from above. Deep-sea bacterial mats form living carpets on the seafloor around vents and seeps, creating the foundation for entire ecosystems. These mats can be incredibly thick, sometimes several feet deep, representing billions upon billions of individual bacteria all working together to process chemicals and create the energy that powers their communities. The deep-sea blob scalpin looks exactly like its name suggests, a gelatinous blob that seems almost too soft to be real. But this apparent fragility is actually its greatest strength. Its jelly-like body allows it to survive pressures that would crush rigid organisms, while its pale pink color makes it nearly invisible against the pale sediment of the deep seafloor. Deep-sea sound travels differently than surface sound, creating acoustic environments unlike anywhere else on Earth. The deep sound channel can carry whale songs for thousands of miles, while other sounds are absorbed quickly by the dense, cold water. It's a world where whispers can travel across oceans and shouts fade into silence within meters. The deep-sea pelican eel can unhinge its massive jaw to create a mouth larger than a pelican's pouch, allowing it to swallow prey much larger than itself. Its throat is lined with backward-pointing teeth that ensure nothing escapes once it's been swallowed. It's evolution's answer to the feast or famine existence of the deep ocean. When food is available, eat as much as possible. Deep-sea hydrothermal vents create underwater aurora displays, with minerals precipitating out of the hot water and creating shimmering curtains of color in the darkness. The water around these vents can contain dissolved metals in concentrations that would be toxic to surface life, yet vent organisms have learned to not just tolerate these metals, but to use them as building blocks for their shells and structures. The deep-sea atolla jellyfish has perfected one of the most sophisticated alarm systems in the animal kingdom. When attacked, it creates a bioluminescent burglar alarm, a ring of light that pulses and spins around its body, designed to attract the attention of larger predators who might eat whatever is attacking the jellyfish. It's calling for help using light, broadcasting its distress across the dark ocean. Deep-sea sediment cores reveal the history of our planet in extraordinary detail, with each layer representing thousands of years of accumulated marine snow. These cores contain evidence of asteroid impacts, volcanic eruptions, ice ages, and mass extinctions, all preserved in the quiet accumulation of deep-sea mud. The deep ocean floor is Earth's greatest library, storing information about our planet's past in its sediments. The deep-sea thread-fin dragonfish trails long, thread-like fins behind its body as it swims, these fins covered in bioluminescent organs that create moving patterns of light in the darkness. It's like a living constellation, its light patterns potentially serving as species recognition signals or as lures to attract prey from vast distances in the dark water. Deep-sea methane hydrates, frozen methane trapped in ice-like crystals, contain more carbon than all known oil, gas, and coal reserves combined. These hydrates exist only under the specific pressure and temperature conditions found in deep ocean sediments, and they support unique ecosystems of bacteria and other organisms that can metabolize methane directly. The deep-sea bowerly fish has a transparent head filled with clear fluid, and its tubular eyes can rotate within this fluid-filled chamber to look upward toward the surface or forward toward prey. It's like having a periscope mounted in a transparent submarine, perfectly designed for spotting the silhouettes of prey against the faint downwelling light. Deep-sea wood-boring shipworms can consume entire sunken ships, their specialized bacteria helping them digest the cellulose in wood. These worms can grow to lengths of over 3 feet, and a single piece of sunken wood can support colonies of them for decades. They're living recycling centers, breaking down terrestrial organic matter that finds its way to the deep sea floor. The deep-sea Dana octopus squid is one of the largest cephalopods in the ocean, with arms that can span over 6 feet. Despite its size, it's rarely seen, living in the deep open ocean where it feeds on fish and other squid. Its body is covered in photophores that create complex patterns of light, possibly for communication with others of its species across the vast distances of the deep ocean. Deep-sea fish often have reduced or absent ribs, their body cavity filled with watery tissue that's nearly the same density as seawater. This adaptation makes them neutrally buoyant without the need for a swim bladder, allowing them to hover in the water column without expending energy on swimming just to stay in place. The deep-sea peanut worm gets its name from its habit of retracting its head when disturbed, making it look like a wrinkled peanut. But when it extends its feeding proboscis, it becomes a sophisticated deposit feeder, processing sediment and extracting nutrition from the organic matter mixed in with the mud. It's a living processing plant, turning waste into sustenance. Deep-sea bioluminescent bacteria often live in symbiotic relationships with larger organisms, providing light in exchange for nutrition and protection. These relationships can be so intimate that the bacteria become essentially organelles within their host's body, their DNA sometimes integrating with their host's genome over evolutionary time. The deep-sea cookie-cutter shark's lower jaw is filled with triangular teeth arranged in a perfect cutting ring, like a living cookie cutter. When it bites a larger animal, it rotates its body to cut out a perfectly round plug of flesh, then releases its hold and swims away. Its bite marks are found on whales, dolphins, and large fish throughout the world's oceans. Deep-sea trenches contain some of the most extreme environments on Earth, with pressures over 1,000 times greater than at sea level, near freezing temperatures, and no light whatsoever. Yet even these most extreme places on our planet support life, specially adapted amphipods, bacterial communities, and even fish that have found ways to thrive in conditions that would instantly kill most other life forms. The deep-sea goblin shark can shoot its jaws forward like a projectile, extending them far beyond its head to catch prey. This jaw extension happens in milliseconds, faster than the human eye can follow, turning the normally sluggish shark into a lightning-fast predator when prey comes within range. It's a living jack-in-the-box, hiding explosive speed beneath a seemingly slow exterior. Deep-sea polymetallic nodules grow on the abyssal seafloor like underwater potatoes, formed over millions of years by the slow precipitation of metals from seawater. These nodules can contain rare earth elements crucial for modern technology, but they also support unique ecosystems to bacteria, foraminifera, and other small organisms that depend on the specific chemistry of these metal-rich formations. The deep-sea telescope octopus has eyes mounted on stalks that it can extend far from its body, allowing it to peer around obstacles and spot prey or predators from a safe distance. It's like having periscopes that can be extended in any direction, giving it a huge advantage in the three-dimensional environment of the deep open ocean. Deep-sea fish often have reduced lateral line systems, the organs that detect water movement and pressure changes, because in the still waters of the deep ocean, these sensors would be less useful than in the turbulent surface waters. Instead, many have enhanced chemical sensors, able to detect the faintest traces of food or pheromones in the vast, dilute environment of the deep sea. The deep-sea zombie worm, Ozadax, has no mouth, no stomach, and no gut in the traditional sense. Instead, it has evolved a unique way of life, using acid to dissolve whale bones and absorb the lipids stored within them. Different species of zombie worms specialize in different types of bones, some preferring ribs, others vertebrae, still others the dense bone of whale skulls. Deep-sea seamount ecosystems can take thousands of years to develop, with slow-growing corals and sponges creating the three-dimensional structure that supports entire communities. These ancient communities are incredibly fragile. A single pass by a deep-sea trawl can destroy centuries of growth in a matter of minutes, making seamount conservation one of the most urgent challenges in marine biology. The deep-sea giant Larvician builds houses out of mucus, complex, multi-chambered structures that can be over 3 feet across. These mucus houses serve as both shelter and feeding apparatus, with intricate filters that separate different sizes of food particles. When the filters become clogged, the Larvician abandons its house and builds a new one, creating a constant rain of discarded mucus houses that provides food for other deep-sea organisms. Deep-sea hydrothermal vent chimneys can grow several feet in a single year, built by the precipitation of minerals from the hot, chemical-rich vent water. These chimneys can reach heights of over 180 feet, creating underwater skyscrapers that support entire cities of life. Each chimney has its own microclimate, with different temperatures and chemical compositions that attract different species. The deep-sea dragonfish has a stomach that can stretch to accommodate prey nearly as large as itself, and its body is so elastic that it can appear to double in size after a large meal. In the food-poor environment of the deep ocean, the ability to take advantage of any feeding opportunity, regardless of the size of the prey, can mean the difference between survival and starvation. Deep-sea fish often have hearts that beat incredibly slowly, sometimes as few as 1 or 2 beats per minute. This slow heart rate is an adaptation to their low-energy lifestyle and the low-temperature environment of the deep ocean. Their blood moves slowly through their bodies, carrying just enough oxygen to support their minimal metabolic needs. The deep-sea swallower eel can unhinge its jaw and expand its throat to swallow fish larger than itself, sometimes so much larger that the swallowed fish is clearly visible through the eel's transparent skin. Occasionally, the swallowed fish is so large that it kills the eel, but this extreme feeding strategy has allowed swallower eels to survive in the nutrient-poor environment of the deep ocean. Deep-sea whale falls create succession communities that change over time as the whale carcass decomposes. First come the sleeper sharks and hagfish that feed on the soft tissue, then the bacterial communities that break down the remaining flesh, then the bone-eating worms that can persist for decades, and finally the bacterial mats that process the chemicals leaching from the bones. The deep-sea football fish gets its name from its inflated, ball-like appearance, but it's actually a highly specialized predator with one of the most efficient lure systems in the deep ocean. Its bioluminescent lure can be extended to nearly twice the length of its body, allowing it to attract prey from great distances in the food-sparse environment of the deep sea. Deep-sea glass sponge gardens create underwater forests that can persist for thousands of years, their delicate silica spicules weaving together to form structures of incredible complexity and beauty. These gardens support diverse communities of fish, crustaceans, and other invertebrates, creating biodiversity hotspots in the otherwise sparse deep-sea environment. The deep-sea fan sedival has evolved one of the most extreme examples of sexual dimorphism in the animal kingdom. The tiny male fuses permanently with the much larger female, becoming essentially a sperm-producing appendage. This strategy ensures that reproduction can occur even in the vast, sparsely populated environment of the deep ocean, where finding a mate might otherwise be nearly impossible. Deep-sea bacterial communities can process chemicals at temperatures that would cook most life forms, using thermostable enzymes that remain functional at temperatures exceeding 100 degrees Celsius. These extremophile bacteria have revolutionized our understanding of the limits of life and have provided crucial enzymes for biotechnology applications. The deep-sea bigmouth bass has a mouth so large that it makes up nearly half of its total body length, and its throat is lined with backward-pointing teeth that ensure captured prey cannot escape. This extreme adaptation to the feast-or-famine lifestyle of the deep ocean allows it to capture and consume prey that would be impossible for a more conventionally proportioned fish. Deep-sea mud volcanoes create underwater landscapes that look like alien worlds, with cone-shaped mounds rising from the seafloor and venting cold, chemical-rich fluids that support unique bacterial communities. These mud volcanoes can be hundreds of feet tall and support their own ecosystems, completely separate from the surrounding deep-sea environment. The deep-sea stoplight loose jaw can produce both red and blue bioluminescent light, giving it a significant advantage in the deep ocean where most organisms can only see blue light. It can use its red light like a private flashlight, illuminating prey that can't see red wavelengths, essentially hunting with invisible light in a world where light is the ultimate weapon. Deep-sea fish often have expandable pharynges, throat cavities that can be inflated like balloons to create suction for feeding. This adaptation allows them to vacuum up small prey items or suck larger prey directly into their mouths, an efficient feeding strategy in an environment where every calorie counts and prey encounters are rare. And here, in the deepest, darkest, most patient places on our planet, we find perhaps the most important lesson the ocean has to teach us. Life doesn't always need to be fast, bright, or dramatic to be successful. Sometimes the greatest victories come from simply persisting, from finding ways to thrive in conditions that seem impossible, from adapting so completely to your environment that you become one with it. The deep sea reminds us that most of life on Earth exists in conditions we can barely imagine, following rhythms we're only beginning to understand. These creatures have mastered arts we're still learning to see how to live efficiently, how to make the most of limited resources, how to find beauty and purpose in darkness, how to cooperate in the face of scarcity, how to be patient in a world that rewards persistence over speed. Think about the glass sponges, growing for thousands of years, never rushing, never hurrying, simply adding one silica spicule at a time to their ancient skeletons. Consider the deep-sea fish that can survive for months without food, their bodies operating on such minimal energy that they barely seem alive, yet perfectly adapted to their environment. Imagine the bioluminescent creatures creating light without heat, without waste, with an efficiency that puts our best technology to shame. These are the masters of sustainability, the champions of making do with less, the artists of finding beauty in the most unlikely places. They remind us that success isn't always about being the fastest, the brightest, or the most aggressive. Sometimes it's about being the most patient, the most efficient, the most cooperative. The deep ocean is a world of collaboration rather than competition. The bacteria and tube worms working together at hydrothermal vents, neither able to survive without the other. The bioluminescent bacteria living inside fish, providing light in exchange for nutrition and protection. The siphonophores that are not individuals but communities, hundreds of specialized organisms working together as one. In our hurried, brightly lit, loudly competitive surface world, there's profound peace to be found in contemplating the quiet wisdom of the deep sea. Here in the largest habitat on our planet, success is measured not in speed or brightness, but in persistence, efficiency, and the ability to find your niche and thrive there, no matter how unlikely it might seem. The deep sea is still revealing its secrets to us. Every expedition brings new discoveries, new species, new ecosystems, new ways of life that challenge our understanding of what's possible. We've explored less than 5% of our ocean, which means that 95% of our planet's living space remains a mystery, waiting to be discovered. There are creatures down there we've never seen, ecosystems we've never imagined, solutions to problems we haven't even thought to ask yet. As you settle into sleep tonight, perhaps you can carry with you some of the deep ocean's profound tranquility, the patience of creatures that measure their lives in decades or centuries rather than days or years, the efficiency of organisms that waste nothing, use everything, find sustenance in the most unlikely places, the quiet cooperation of communities working together in the darkness, creating light, warmth, and life through their collaboration. The deep sea teaches us that there's more than one way to be successful, more than one way to be beautiful, more than one way to create light in the darkness. In a world that often feels chaotic and rushed, there's something deeply comforting about knowing that in the vastest spaces on our planet, life moves slowly, deliberately, sustainably, finding ways to thrive that we're only beginning to understand and appreciate. Thank you for joining me on this journey into the blue heart of our world, this exploration of the patient, persistent, quietly miraculous realm that covers most of our planet yet remains largely hidden from our everyday awareness. Whether you're listening from a bustling city where lights never dim, or from a quiet rural area where you can see the stars, from the bright energy of morning or the gentle stillness of evening, you're part of a global community of curious minds, people who find wonder in the natural world and peace in understanding our place within the larger story of life on Earth. The deep sea reminds us that we are all connected by the same water, the same blue planet, the same ancient rhythms that have been sustaining life for billions of years. The water in your body once fell as rain, flowed in rivers, and very likely spent time in the deep ocean, part of the great circulation system that connects all life on Earth. You're part of the ocean's story, and the ocean is part of yours. If this gentle exploration of our planet's deepest places brought you a moment of peace, if it helped you see the extraordinary in what might seem like an empty, dark void, if it reminded you that patience and persistence are among nature's greatest virtues, please consider subscribing so you never miss these quiet journeys into the wonders of science and nature. And if you feel comfortable sharing, I'd love to know where in the world you're listening from, what drew you to tonight's deep sea journey, what you found most surprising or comforting about life in the ocean's deepest places. Until next time, may your dreams be as deep and peaceful as the ocean itself, as patient as the creatures that call the abyss home, as wonder-filled as the bioluminescent displays that light up the darkness in the deepest places on Earth. Sleep well wherever you are in our beautiful watery world, and remember that even in the deepest darkness, even under the greatest pressure, even in the most unlikely places, life finds a way to create beauty, community, and hope. Sweet dreams, and good night, from the depths of our blue planet.